Greetings everyone, today I'll be presenting our work on Origami-Inspired snap-through bistability in parallel and curve mechanisms through the inflection of degree 4 vertexes. So let me explain some of the keywords in our title. First up, origami is the transformation of a 2D structure into a 3D structure. Bistability can be considered as a structure where they will only be stable in one of two states, and the step-through effect between these two acts as the energy barrier which separates these two stable states. For the parallel and curve mechanisms as shown here, the parallel mechanisms that we'll be focusing on is the Serres mechanism, which moves in a linear fashion, and the other one is a curve mechanism, which will be useful as a manipulator or grasping arm. For the degree 4 vertexes, it looks like this. It is a vertex with 4 creased lines, and usually when the inflection happens, the vertexes will move into or out of plane, and then the creased lines will actually invert. So from a mountain flow, they'll transform into a valley flow. Now all of these components will be presented in our work here as is shown in the figure on the right into these two mechanisms. One question we could ask is, why do we want to have origami in our structure? Well, there are several advantages to origami. First up, in that origami structures are very foldable, and this can help in its transportation, where it can be transported in a single state and then subsequently folded or unfolded for deployment for its particular function. Such as in this case, a Serres structure is used to deploy a needle. Yeah, in this case, probably a Miura type unfolding is used to deploy satellites. Next up, origami is quite unique in the sense that it has both rigid and soft properties, rigid facets and flexural hinges, which is soft, and this can allow some interesting bistability effects to occur, which can then be applied for safety or energy efficient loading. Origami structures are also much simpler to their counterparts. This allows the fabrications to be different. Most of the time it is easier to fabricate, and also it makes it more possible to fabricate at smaller scales. Stability, as mentioned earlier, can have some benefits, for example in loading and unloading. So for example, in this particular structure here, when the cylinder is fully unfolded, it is able to bear high loads as shown here. It is able to bear 500 grams. However, if it is not fully unloaded, then it does not have this strong property and is rather compliant, so a 100-gram weight will flatten the entire structure. So these bistable properties can be seen throughout many different structures as shown here, but some unique properties that we want to look at more similar towards this bistable twisted tower structure is because that the bistability itself is incorporated in the crease pattern design itself. And when we look at these bistable structures, generally we could look at them as having an energy barrier such as a non-fully deployed state or fully deployed state. And in between both there is an energy barrier, and this energy barrier is what dictates the two separate states that we're looking at. So the twisted tower origami structure, our structures are also shell-based structures, one being the Serres mechanism, which is a parallel mechanism, and the other one is a curve mechanism. So for the parallel mechanism, like the twisted tower, it moves out in a linear fashion. However, unlike the twisted tower, there is no rotation coupled with the linear motion. Now for the deformation of these two structures, one moves along a straight path, one moves along a curved path, both of which can be considered as a predetermined path, and the displacement across 2 points should be controlled by a single actuation. And we use the bistability incorporated into these elements, these shell elements, to compartmentalize the different motions within that path. Now the degree 4 vertex for both structures are shown here. So for the Serres mechanism, the vertex is here, it is this point here, as well as for the curve mechanism, the vertex is shown here. The crease lines are all shown in dotted yellow lines. Here we compare the differences between the continuous structure versus the bistable structure. By looking at the crease pattern, it is quite clear to see which are the elements that contribute to the bistability. We should note that our origami structure is not really a pure origami structure, as we do use some cutting and gluing to build the structures. So the black lines represents areas where the structure is cut. Red lines represents mountain flows and blue lines represent valley flows. Currently the material tested is made of paper, however it can be replaced with any other material such as plastic. For the testing of the bistability properties, we attach a stick as indicated by the green arrow to the top facet, and the base facets are all anchored to the base. The machine that we use for testing is an Instron uniaxial stress strain testing machine. So this makes the linear motion move up and down, and then we collect the the strain response, the stress and strain responses, which is the force and displacement. Comparing between the bistable Serres mechanisms and the continuous Serres mechanisms, we can see, comparing the blue line versus the red line, that there is a clear difference indicating that there is a bistability. In the inset, is a blow up of the red line. The initialization conditions is indicated by point number 10. From traveling from point 1 to point 2 along the path 3, 4, 5, the structure is being compressed. At 3, 4, and 5 is where we suspect the snap through to have occurred, and the initial loading and then bending of the facets as well. At point 4 is where we think the critical load is achieved, when the structure snaps through at that point, which drastically causes the loads to decrease. From point 2 to point 1, the reverse occurs and the the snap-through structures refold itself. Given the experimental observations, we would like to propose some theoretical analysis. We utilize some geometry. Looking at our structure, we've identified a few key points, namely P1, P2, P3, and P4, and the two facets of interest, which is highlighted in yellow and blue. Now we need to make a few assumptions, granted that they are very gross assumptions. So the first two things that we would like to assume is that 1, the facets are rigid, and 2, the facets can intersect with each other. Now utilizing geometry, the points P2, P3, and P4 can be identified, and then subsequently the points P1 and P1 prime can be calculated. Given the points P1 and P1 prime, we can then get the intersection point Pi. Now if we make the assumption, if we were to look at how the length changes, maybe say from P1, P2 to Pi, P2, then what we observe is this graph here. So what this graph tells us is that this current consideration is not fully correct, simply because at point 0, the strain should not be at the maximum. Now that we have the position of Pi, we can observe how Pi moves as the structure is compressed. So Pi moves outwards as the structure is compressed. When this point Pi moves, we can then look at how does the length change, maybe say comparing P3 Pi. So if we do that through these equations here, what we'll get is this graph here, and this seems to agree quite well with the snap-through positions that we have observed experimentally. Another experiment that we considered, which is shown in the video on the right here, shows the snap-through effect happening. So below is a magnet which attracts it, and only once our finger pushes the structure past the snap-through point, it then snaps through flat. So this snap-through energy barrier is here. If the snap-through energy barrier is not passed, then there are two actuation states, one here and one here. These actuation states have the same magnetic actuation, so here the actuation heights are greatly different. While the theoretical analysis may not be very comprehensive, it still gives us a good first step as to how to look and how to understand these structures. Experimentally, however, there are many things that we can try. So for example, if we look at size variations, we can change the size of the structure. However, because the thickness of the structure does not change, then this affects the flexural rigidity of the facets as well as the hinge joints. So from here we can see that it is possible that there is an optimal position, for example the 30 mm size here, where it gives us the highest energy barrier. And we also tested adding of more vertices on the right. So when we add an additional vertex, seeing the red line here, we can actually have 2 peaks instead of 1. We also modified the vertexes. So by either retracting or extruding the vertex, we can tune the amount of bistability that we can get. So for example, if we retract the vertexes, the structure tends to lean more towards the continuous type structure, losing the snap-through. However, unlike the continuous structure, it still has some form of a resistance. So it is more continuous, but it retains some stiffness from the bistability state. Whereas if we extrude the vertex, then it becomes much more of a strain loading structure, where the energy barriers are very high. However, if we extrude the vertex excessively or too far, then the bistability can be lost if the energy barrier is too high. Next, I will talk about the curved origami structures. Well, curved structures that are capable of controlled bending are popular in applications that require accessing and maneuvering within tight and narrow confined spaces. Such structures are often compliant, flexible, and capable of large deformations. However, this limits their ability to exert and bear large forces. Bistable curved origami structures can be compact and able to transport through narrow spaces before it is actually deployed into a functional state. Here we design a crease pattern shown in figure 4a that gives rise to a bistable origami structure that can be easily transported into its undeployed compact state and then deployed into a rigid curved configuration of tunable bending angles. As a proof of concept, we fabricated the structure using a traditional A4 paper. Similar to the parallel mechanism, this structure can be deployed in a similar manner into a curved rigid structure via the snap-through switching actuation once it bypasses the energy barrier, in which the valley folds of the structure will snap through and then it will become a rigid facet, as shown in the second state, figure 4b. The degree 4 vertex lies on the valley fold, and the crease around these structures around these vertexes also inflect locally in a similar manner when the curved crease structure is deployed. The deployed curve structure is compliant around the rotation axis up to a specific angle at which it is unable to rotate further due to the inherent structure as shown in C. A compression test is performed using the same instrument testing machine where the structure is observed to be more structurally stable and able to bear greater loads in the deployed state. This is in figure D. The structures can be used as a constrained rotational hinge joint, which is useful in applications where bending beyond a certain angle is undesirable due to functional or safety reasons. This minimum bending angle can be tuned by modifying certain parameters of the underlying crease pattern shown in A. In its undeployed state, the structure can bend along its rotational axis in both directions within a certain range of angle. Bending beyond this range of angles will cause the structure to exceed its snap-through energy barrier, causing the structure to deploy. As observed in A, the structure was bent along its axis towards the left, while it is expected for the structure to pop and switch at a certain angle upon exceeding the snap-through energy barrier. We instead observe that the structure is able to gradually deploy until it reaches the minimum bending angle. This could be attributed to the paper's compliance, which result in a less obvious snap-through behavior. Due to the bistability of the deployed structure, the structure did not return to the original state in the absence of external loading. The structure can also be deployed in the opposite direction as shown in B. Similarly, the structure will retain its deployed state. In its complete deployed state, the structure can be employed as a hinge joint with controlled bending in C. The structure does not bend further beyond this angle despite the continual increase in loading force. Releasing the external forces causes the structure to unbend towards its initial state along the same pathway, similar to that of a typical hinge. With that, I would like to summarize that in this book we have presented one particular design which utilizes inflection of degree 4 vertexes for linear as well as curved mechanisms. Now we showed the experimental characterizations of some of the mechanical properties and provided a theoretical hypothesis as to how these bistability structures are being conferred their bistability. I think in the future, more work can be applied for these structures for various other applications in mechanical structures or robotic applications. These are the references used in this presentation. Thank you for listening. This is the end of our presentation. We would like to give some acknowledgements to our lab members, in particular Meng Ya for helping us in the organization of the conference, and to our Professor Prof Ren for his guidance throughout this entire work. We would also like to acknowledge the grants as shown in this slide. Thank you.